Yeah, let's see here.
Where did that come from?
All right. I'll begin with a word of prayer. No CFAWs. Yes. All right. Let me pray. There are no CFAWs, right? That's just it. Dear Heavenly Father, we thank you for this day again. I thank you for this class and this opportunity we have to meet and study your creation. Just pray that you'd give us understanding today, Lord. In your name I pray, Lord Jesus. Amen. All right. So, first of all, my apologies to Team C. I still haven't made your video. But I haven't forgotten about it, so hopefully tonight I'll get that made for you guys. So you'll have hints similar to teams A and B. And I'll look through all the teams again and see if I can make any more hints to help you guys. But anyway, so today we're talking about, let's see here, multivariate analysis. But really, we're just talking about the multivariate power series. And so, a little bit more than that, we're also going to talk about how to approximate a nonlinear map by its best linear approximation. All right? So, yeah, perhaps I should start there. So, I guess first of all I need to give you a definition. If F is a mapping from, say, Rn to R, all right, then partial F partial x sub j at the point P is equal to the limit as h goes to 0 of F of P plus Hej minus F of P all divided by H. That is the definition of the partial derivative with respect to the jth variable in n dimensions for a function that's real valued. And I mean, let's see here, how can I, another way to say this is what you're doing is you're taking the derivative with respect to t of like f of p plus t times ej, right? You're taking that derivative and then you're setting t equals to 0. That's another way to look at the partial derivative. So what you're studying is, what is p plus tej anyway, guys? Let me just kind of like demystify this whole formula here. What is the mapping t maps to p plus tej? What is this? If I call this thing gamma of t, can you describe that path? What is that path? What's a path which is going through p plus tej? What's gamma of 0? Yeah, gamma of 0 is p. And gamma prime of 0 is, like what happens when we differentiate this? P is constant, right? And we just get e sub j, right? So what the partial derivative does is it calculates the change in the function in the jth coordinate direction. This is, of course, a directional derivative. If you've had calculus 3, you've talked about that, right? So partial derivatives are special directional derivatives. Okay, so I think most of you have had Calc 3 from what I remember, maybe everybody here, or at least you're taking it. If you're taking it, by golly, by now you've done partial differentiation out the wazoo, right? Yeah, so this is not mysterious, although the n-dimensionality of it might be. So let's calculate a couple of these. Let's see here, so example 1. What would be if I had f of xy equals to, say, xy squared plus e to the xy. Calculate partial f, partial x, what do we get? Differentiating, I get y squared and then plus e to the xy chain rule, partial x of xy. So lo and behold, we get y squared plus y e to the xy. Because the partial derivative of xy with respect to x is just y. I mean, what I'm using, of course, is the intuitive interpretation of my definition above, which is to partial differentiate with respect to xj. You differentiate with respect to xj as if it's calculus 1, and all of the other variables you think of as constants, right? That's what the practical application of that limit definition means. So partial f partial y here is, 2xy, right? And then chain rule on that brings down, instead of x, it brings down, instead of y, it brings down x, e to the xy. All right. One more example here. Example 2, suppose you had f of x equals to x dot x for x in Rn. What's the partial derivative of the dot product here? What if I calculate partial f, partial x I of this? What is x dot x? Well, it is there's a smart way and a dumb way to do it. I'm going to do it the dumb way, if you guys don't mind. So the dumb way is just write it out, look at it. What's the answer? So like, here's the thing. Partial x j, partial xi, what's that equal to? 0 if I not equal to j, right? 1 if I equals to j. What is that? I mean, we have a name for that. Yeah, this is the Kronecker delta, for what it's worth. But the larger point here is everything here is 0, right? Except for what? Except for the ith one, where we get what? We get 2x sub I. There you go. That's you're like, your 2 and your partial look an awful lot alike. I'm like, well, I guess you shouldn't take calculus 3 with me. Or perhaps it's already too late for you. It's already happened. I don't know. But all right, so there you go. Partial differentiation. Now, oh, man. So next up, let's consider mapping from Rn to Rm. All right. And I'm not assuming from the outset here, guys, that it is oh man, excuse me, guys. You know, I woke up this morning and I was not at all feeling like a cough, and I was like, oh, I'm past it, yay. Yeah. False. So this might be nonlinear, all right? Possibly a nonlinear map. And so we'll call the mapping F, right? Big F. So for instance, so example, before I give you the definition, you might have something like f of, say, xyz equal to x squared plus y squared, comma, y squared plus z squared, comma, x squared plus z squared, like that. For instance, that would, I probably should throw in another one here. My third one, I'll do xyz, okay? There. So that would be a mapping from what to what? The input is 3-dimensional, right? The output is 4-dimensional. Is this linear? No, it's got squares in it, right? So it's not going to be linear. Suppose you wanted to approximate this function with its best linear approximation. How would you do that? All right. How would you do that? That's what I want to explain to you. before I do that, though, I need to give you a definition. Definition, f is differentiable with derivative f prime of p which is a mapping itself from, say, Rn to Rm. Excuse me, guys. This is linear. If the following limit exists. So here we go. The limit as h goes to 0 of f of p plus h minus big F of p minus f prime of p times h, all divided by h equals to 0. What I just wrote is nonsense. Tell me why. What's that? But we have 0, but over here? I mean, that's the heart of the matter. You're right. That's the issue. Why is it okay to divide by h here, but it's not okay to divide by h there? What kind of limit is this, actually? What is h? H is in the domain for big F, right? H is, by context here, h is taken from Rn. So we're dividing by an n vector. What does that even mean? I'll tell you what it means. If you see somebody writing that, it means they don't know what they're talking about. So watch out for that. So it's easy enough to fix. You put a norm here, the length of the vector, then it's fine. We can divide by it, right? Anyway, this is, I guess I should give attribution where it belongs. This is the so-called Fréchet quotient. All right, so anyway, obviously I'm not going to test on this in here. At this, I'm going to test on limits in here, obviously, right? Like, nobody wants that, right? I don't want that. You don't want that. But here's the cool thing. When f is differentiable and this derivative exists, the derivative is a linear map, right? So theorem, f prime of p times h is equal to, of h rather. So I'm saying f prime of p is a linear transformation. When we put h into it, we get what's called j sub f of p multiplying by h. In other words, that is aka the matrix, the standard matrix of the derivative map is the so-called Jacobian matrix at the point P. In the Jacobian matrix, we don't need limits or anything for that. That we can calculate explicitly as follows. So here's how it goes. The Jacobian matrix of f is straight up equal to partial f, partial x1, partial f, partial x2, partial f, partial xn. That's the Jacobian matrix of the Jacobian matrix of a map. It's just that. And you guys know what matrices are. And you also know what partial derivatives are, so this is not a big deal, right? Another way to look at this is it's a stack of gradients. So it's the gradient of the first component function of f, gradient of the second component function of f, gradient all the way down to the mth component function of x. I think of gradients as column vectors, so I owe you some transposes on these. There's another way you could look at it. Let's actually calculate it for my example. All right, so example 3. And we'll calculate this example both ways, all right? So what's the Jacobian of f for this guy right here? So I do partial f, partial x, partial f, partial y, partial f, partial z. I think that's it, right? I've only got 3 input variables, so I get 3 columns in my Jacobian matrix, right? And then, let's see here. So x derivative gives me 2x, 0, 2x, and yz. I'll let you guys tell me the second column while I cough. Just a tickly cough now is the worst. This I would test on, so. Like, can you find the Jacobian matrix? So what do you guys got?
2y.
I got a 2y, all right. Then what?
2y.
2y, all right.
0.
Uh-huh.
Z.
xz, very good. How about the third column?
0.
Mm-hmm.
2z.
Mm-hmm.
2z. xy.
Cool. So there you go. That is the Jacobi matrix. Notice that you could look at this as the stack of, this is the gradient of the x squared plus y squared vector. This is the gradient of the y squared plus z squared function, rather. This is the gradient of the x squared plus z squared function. And this is the gradient of the xyz function, right? Transposed. Where here I'm suggesting that the gradient of f means partial f, partial x, partial f, partial y, partial f, partial z for f, a mapping from R3 to R. That you probably saw in Calculus 3, but not with the column notation, right? With like angle bracket or whatever, like the gradient vector field, partial f, partial x, comma, partial f, partial y, comma, partial f, partial z, right? We don't need commas if I stack them vertically, but that is the gradient in this context. So like, it's up to you guys, like how you want to look at finding the Jacobian matrix. You can either find it from taking partial derivatives, right, of the map. Did you guys see a sleight of hand I did right here? What did I just do? I defined the partial derivative for a function, a real valued function, right? But what kind of partial derivatives am I taking here? I'm taking partial derivatives of a vector valued function, aren't I? See that? It's kind of sneaky. Like technically, this is not the partial derivative I defined at the start of class, because the start of class, I defined a partial derivative for a function that takes its values in R. But the component function, but f takes its values in this case, where? R4. But the partial derivative for a function that takes its values in R4 is simply defined component-wise. So like partial f, partial x, j is by definition partial f1, partial xj, partial f2, partial xj, partial f3, partial xj. I shouldn't have even told you about this. You wouldn't even noticed it. You'd have just accepted it and thought that I'd already defined it, maybe, if I'm lucky. But technically speaking, that is a theorem. Actually, technically speaking, I need to define the derivative, partial derivative with respect to a vector valued function, I suppose. But the definition would be exactly the same as the one I wrote, except instead of letting the function be real valued, you'd let it be vector valued. But the same limiting process would be done as we did at the start of class. Are we good? I mean, I know I'm saying a lot of words, but let me like centralize the question down to a simple question. Can you calculate a Jacobian matrix? If I give you the function and I say find the Jacobian matrix, I think you guys can do that, right? It's not bad. Now what do we do with it? So here's the theorem. F of, let's say f of, I'll use r for the variable. F of r vector is approximately f of r naught plus the Jacobian of f at the point r naught times r minus r naught. This is how you find the best approximation, the best linear approximation to a nonlinear function. Let's actually do it for my example 3 here. So like example 3, we'll just call it example 4. So let's linearize the map from example 3. And let's do it at the point. Let's do it at the point 1, 2, 3. That way we can see what's going on best, probably. 1, 2, 3. All right. This is the. This would be a generalization of the concept of, say, finding the tangent line, right? We found the tangent line in calculus 1. Tangent line in calculus 1, best linear approximation to a graph in, you know, what is that? Well, 2 dimensions, I suppose. And then in calculus 3, you found the best tangent line to a space curve, right? Something like that, tangent line of a path. Well, this is past that. This is the best linear approximation to a map. I guess that corresponds to some sort of like tangent plane in higher dimensions or something, but that's not really helpful to you guys, right? Because visualization kind of fails once we get more than 3 total variables between the domain and the codomain. Anyway, so what we got? So this is my quote-unquote r naught, and I'm thinking of r here as just being x, y, z, right? So like r minus r naught is actually, you know, like x minus 1, y minus 2, z minus 3. It's a column of differences. All right, let's see, what else can I unwrap here? So what's the Jacobian of f? Oh man, at 1, 2, 3, you guys help me out. We got to plug 1, 2, 3 into that, right? So I got what? I got 2, 0, 2. Y times z is what? 2 times 3, 6. 2 times y. 2 times 2 is 4. 4. 0. Xz is 1 times 3, which is 3. We got 0. 2 times 3 is 6. 6. X times y is 2 here. All right. And so here it is. The value of our function at x, y, z is approximately, oh, I need to figure out what is f of 1, 2, 3 equal to, right? That's f of r naught. I need that to start with, right? So what would that be? I forgot my, I've got 1 squared plus 2 squared, comma, 2 squared plus 3 squared. And then 1 squared plus 3 squared. And then 1, 2, 3. So what did that work out to? What do we got here? Looks like a 5. 9 plus 4, 13. 10. And 6. That's the value of the function at the point of the approximation. So we've got 5, sort of the point of tangency, if you like. So 5, 13, 10, 6, plus the Jacobian matrix, which I have right there. 2, 4, 0, 0, 4, 6, 2, 0, 6, 6, 3, 2. And then I multiply that by my difference vector. X minus 1, y minus 2, z minus 3. And there you go. That's it. That's how you do it. That's how you approximate a function of several variables, even when the value is a vector. You just take partial derivatives, form the Jacobian matrix, plug in the point you're interested in, multiply by the difference vector, add the value of the map. And that's the formula. Simple as that. And I'm not joking. I really do think this is simple. All right. Now I could multiply this out. I don't know if that would be helpful or not. I'm not going to, but of course, oh fine, I'll start. So in my other notation, this would look like 5 plus 2 times x minus 1 plus 4 times y minus 2, comma, well, two things, which I don't have room to write everything here, so I'll just skip the middle two. And then 6 times x minus 1 plus 3 times y minus 2 plus 2 times z minus 3. Okay, enough of this. So, excuse me, guys. Oh. Any questions? No? All right, so do you guys remember the multivariate power series from Calc 3? You did power series in calculus 2, remember? Sine, cosine, exponential, unending polynomial. Well, they're not even polynomial, right? They're past polynomial approximations for functions. These power series, these unending sums of power functions, which give you exact formulations of all your elementary functions in terms of series. So you remember when we did that in calculus 3? I mean, well, my question, it's a meaningful question if you took my calculus 3, but if you took anybody else's calculus 3, I would wager they did not bother talking about the multivariate power series. Why? Why would they not talk about the multivariate power series? Why would other instructors not talk about the multivariate power series? It's simple. They accept the pedagogy which is based on using a book. I do not. And I was taught by people who accepted the pedagogy of you use what's in the book, not what's logically should be there. And so when I got to grad school and I needed the multivariate power series, I didn't know there was such a thing. But then I talked to Europeans, they're like, what, the multivariate power series, from calculus. And I'm like, no, I don't know the multivariate power series from calculus. I've read every stupid page in Stewart. It's not there, But there is a multivariate power series. Here it is. Oh man, rats. This is the two-dimensional formula for it. Oh, phooey. Well, is it though? All right, I'm going to try to adapt my formula here. So your notes are my best attempt at the moment, guys. Like there's still room for improvement in these notes, obviously, here and there. This is probably one of those spots, because what I really want to tell you at the moment is the honest to goodness full multivariate power series formula in all of its glory. And so I'll attempt it. I think I can get it here. So here's what it is: f of x1, x2. Xn, all right? It's equal to the summation n equals 0 to an... Oh, see, that's the unfortunate thing. Rats. Let me put an m here, if you don't mind, because I don't want this n and that m to be the same. So oh, you know what I'll do? I'll do something more annoying. I'll use a big N for dimension here. There we go, big N for... This is f... oh man, big Rn to R. Because I do like to use the n for the power series. So n equals 0 to infinity. Maybe I could use a k here. I don't know. You're like, just do something. Okay, fine. So sum I1 equals 0 to n. Sum I2 equals 0 to n. Da, da, da. Sum In equals 0 to n. 1 over n factorial. Then the nth partial derivative of f with respect to the variables partial xi1, partial xi2, partial xin. That's this is all evaluated at a, all right? And then times xi1 minus ai1, xi2 minus ai2. So what I have in the notes is almost as general as what I want. And I just want to state it for you. I'm not going to prove this or anything. I mean, I will tell you how it's proved. The proof is simply just to use the Taylor's theorem that you have in Calculus 2 and to basically substitute in a multivariate function into that and to expand that term by term, essentially all it is. And it's like multivariate chain rule and some relatively simple arguments derive this. It's just, it looks beastly. Now here A is the point of tangency we're talking about. Well, A is the center of the approximation. So like A here is A1, A2, da da da, AN, all right? So now that I got that out of my system, because I just wanted to say what it is concretely, we're not really going to use this. What we're interested in are just the first three terms. The first three terms in this. So the first three terms in all this, what happens, what's the lowest order term from all of this? So the first three terms are just this. F of A, all right? And then plus the gradient of f at A, dot product with x minus a in my current notation. X and a are both vectors here, okay? They're n vectors. And the gradient is, you know, also a vector, right, of partial derivatives. And then what you have is what I might call q sub f of x minus a. And then plus dot, 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 dot. So this right here is actually a quadratic form. Going back to last class, that's a quadratic form. Let me be more explicit. So the gradient of f here, you guys learned that essentially in Calc 3, most of you. If you didn't, I'm sorry. You really should have learned that in Calc 3. Sorry. I'm an idiot. Partial f, partial x1, partial f, partial x2, partial f, partial xn. Of course, you mostly didn't do stuff at n dimensions too much in Calc 3, maybe just here or there. But really, it's the same as what you did in 2 or 3 dimensions. So that's the gradient of the function, right? So definition, A is critical point of f if the gradient of f at A is equal to what?
Zero undefined.
0. Yeah, 0 or undefined. Very good. So I wrote gradient of f. So like I've taken, well, fair enough. Yeah, undefined is the other possibility. But, yep. Excuse me. I'm not going to be so bold as to try to like study the undefined case in today's lecture. You know, like I'm assuming f is smooth, like it's got us enough derivatives for us to do this all day long. So that's a critical point. what does the multivariate power series look like at a critical point? So here, this makes the following formula true. F of x equals to f of a, right, plus q of x minus a plus things, right? But the things that's missing here, these involve higher powers of components of x minus a. So they involve cubes or fourth powers or fifth powers or higher still powers of x minus a, right? So logically think about this. What does this mean at a critical point? How to describe the behavior of a function near a critical point? What's it look like? What's it dominated by? These are all stupidly small, right? If you're close to a, we're talking about some number less than 1, right? And it's raised to a high power, like a fifth power, third power, fourth power, right? And the closer you get to a, the worse this gets, right? Clearly, for the most part, these are dominant, right? Those dominate the behavior of the function near a for a critical point. So we can analyze, right? We can decide whether or not f of a is a maximum or a minimum or whatever based on how that quadratic form behaves. How does the quadratic form behave? It's a quadratic form. We can use the real spectral theorem. We can calculate the eigenvalues and eigenvectors of it and decide this issue, right? So the matrix of that Q looks like the following in 2 dimensions. It's just fxx, fxy, fxy, fyy. This is n equals to 2. N equals to 3. The matrix of the quadratic form has the form fxx, fxy, fxz. You're like, hey, there's another notation I don't know because I never had Calc 3. Sorry if you're that person. I will talk to you. But this just means second partial derivatives with respect to x and x or y and z or so forth and so on. This means this is just notation for, like generally speaking, Q is just the matrix that's formed by partial squared f, partial xi, partial xj, right? That's the matrix of the quadratic form. The ijth component of it is the I partial derivative of f and the jth partial derivative of x in that order. Partial differentiation is commutative, so this is a symmetric matrix, which means the real spectral theorem applies, and we got this. So do you guys, now in Calculus 3, I'm surely, you had the second derivative test, yes? Was there a first derivative test in Calculus 3? Search your heart. There was not. Why is that? Why is there no first derivative test for Maximans in Calc 3? So in Calculus 1, you can either come from the left or from the right, right? So you can judge whether it's going up and down or if it's going down and then up, right? But for Calculus 3, as you're approaching a maximum or a minimum, you have infinitely many different directions to check, right? So it doesn't make a very practical test. That's one way to look at it. Well, let's look at n equals to 2. What are the eigenvalues? Eigenvalues of Q sub f for n equals to 2. Can you tell me what they are? So here's Q sub f. We have the fxx, fxy, fxy, fyy. What are the eigenvalues? Did you know that the eigenvalues of a 2 by 2 matrix we can calculate directly using the one of the problems we had on the test? So we had a formula. The trace is the sum of the eigenvalues, right? So first of all, it's a symmetric real 2 by 2 matrix. We know that there are 2 eigenvalues. They're both real, right? So, you know, lambda 1, lambda 2 are elements of the reals, right? And what can we tell you? These eigenvalues for this matrix, what can we tell? Well, certainly the trace is what? It's lambda 1 plus lambda 2, right? But it's also equal to fxx plus fyy, right? And the determinant of the quadratic form is lambda 1, lambda 2, right? Which in terms of partial derivatives is fxx fyy minus fxy squared. Now if you remember your calculus 3, you should recognize what I just wrote as the quote-unquote big D of the second derivative test, right? What does the formula for Q look like in eigencoordinates? What is QF? You know, if I look at QF in say H comma K, where I'm supposing that x minus, oh good grief, language, x minus a1 y minus a2, yeah, y minus a2 is equal to, like, you know, h times eigenvector v1 plus k times eigenvector v2. In other words, I'm supposing h and k are the eigencoordinates with respect to, it's a little bit shadier than that. I shifted coordinates too, but anyway. So this would be something like, you know, lambda 1 h squared plus lambda 2 k squared. It's a little bit different than what we've done before because I'm shifting, right? I mean, it's, you notice I've got like a difference of x and a, and I'm saying I just have, I'm using h and k for like differences. They're the eigendifferences, perhaps you could say. But anyway. If I instead called this like delta x and delta y, maybe it would make more sense to some of you. I don't know, but let me not belabor this. We don't have enough time for me to unravel what I'm saying. But that's the formula in eigencoordinates, right? So you tell me, min or max? When would this be a minimum? When would this be a maximum? What's the story? So again, going back to the, you know, the basis for this, the value of the function near the point is the value of the function at the point plus the quadratic form. So that quadratic form is what? It's going to be adding to the value of the function. If lambda 1 and lambda 2 are both positive, that says that f of, you know, f of a is a local min. If both of the eigenvalues are negative, that says that f of a is local max. Right? If it's a mix, if you have the product of the eigenvalues is less than 0, that says that f of a is neither min nor max. But look at the formulas above for the eigenvalues as they relate to the partial derivatives. So what's going on here? If they're both positive, if they're both negative, excuse me, you'd have that the big D is positive, right? Because you either have plus plus or minus minus. So big D is positive in either one of these definite cases. And in the case of the saddle point, you have the product of the eigenvalues is negative, which makes your big D negative. Yeah? And then to decide local max or local min, it turns out the sum of the eigenvalues, so they either have to both be, If they're both positive, then fxx plus fyy has to be positive. If they're both negative, then fxx plus fyy has to be negative. It turns out when you sort through the details a little bit more, it turns out you can just look at fxx. That's what you see in the calculus books. Just look at a sign of the second partial derivative with respect to x to decide max or min. You could also just look at the second derivative of y. There's actually no need to use the x derivative there. So that's how to prove the second derivative test from calculus 3 using the theory of quadratic forms coupled to the multivariate power expansion idea. This is not the proof, of course, you're going to find in calculus books, because calculus books don't believe calculus students can learn linear algebra. And fair enough, they're probably right, you know, at that stage. Any questions about this? So I'm focusing on n equals 2 for a second. You could try to derive a second derivative test for functions of 3 variables, right? But in order to come up with a test which didn't use linear algebra, you'd have to somehow find a formula that relates the eigenvalues of a 3 by 3 matrix to the second partial derivatives that are in the 3 by 3 quadratic piece of the power series. And those formulas are not that easy to find. That's why you won't find a second derivative test for functions of 3 variables in a calculus book. At least not one I'm aware of. It's quite nasty. But at the level of just looking at this, right? Just look at the multivariate power series. Can you guys tell me, how do you decide if you've got a function in Rn, right? You've got a function in Rn, and you're trying to decide, you know, you're at a critical point. You have a function in Rn. Tell me, what is the condition that you need for f of a to be a local min in terms of the eigenvalues of this? What is it? F of a is a local min at a critical point if all the eigenvalues of this are positive. Because what that means is in eigencoordinates, the formula is just f of a plus positive numbers times squares. All of those get bigger as you get away from 0. So it's a min. If all of the eigenvalues are negative, that makes f of a local max for an n-dimensional function. And if it's a mix of positive and negative eigenvalues, then it's a saddle. It's neither a max nor a min. You can go up or down close to the point of criticality. Criticality, is that even a word? There's one other thing though, right? What if you have an eigenvalue is 0? What then? What then? If there's an eigenvalue which is 0, all of a sudden the door opens to all of this. Then the cubic term could dominate, in principle, over the quadratic term, close to 0, because there is no quadratic term to take care of the change in that direction where the eigenvalue is 0. So all bets are off on the second derivative test if one of the eigenvalues is 0. Just like the second derivative test in calculus 3 is silent in the case that big D is 0, corresponding to the fact that the eigenvalue of the Hessian matrix, by the way, this is called the Hessian matrix, in 2 dimensions. Now, I probably had an example I should have shown you in the notes or something. Maybe not. But I think that's pretty much all I got for you today. If you guys have questions as a team, by all means, send a representative or whatever. I am happy to help. Just don't ask me about the MATLAB commands. I'm useless at the moment. Next year I'll be helpful once you guys give me all the commands. Thank you.